welcome to the Explainer. Today, we're going to talk about a few words you use all the time: work, energy, and power. But here's the thing. The universe has a very specific set of rules for what these words actually mean. And once you understand them, it kind of changes how you see everything around you. You probably think you know what work is, right? We say we're working hard on a project or we're doing yard work. But in physics, the definition is way stricter. And honestly, it has nothing to do with how tired you feel. It's not about effort, it's all about movement. See that crane lifting steel? Yep, that's work. Staring at a textbook, no matter how much your brain hurts? Nope, not work. Getting this one simple difference is really the first step to seeing the world like a physicist. So, how can something that feels like the definition of hard work actually count as zero work in physics? Well, to get our heads around this, we have to look at what work actually means to a physicist. See, in physics, work has two absolutely essential ingredients. You need a force, sure, but you also need displacement. The object has to move in the direction you're pushing it. If there's no movement, like with that wall that won't budge, then there's no work done. That formula W equals F times D tells the whole story. If D, the displacement, is zero, the work is zero. End of story. So it turns out there are a few ways you can apply a whole lot of force and still do zero work. Pushing that wall is one, right? Zero displacement. Another great example is a weightlifter just holding a massive barbell over their head. They're not moving it up or down, so no work is being done on the barbell. And here's a really cool one. When the force you're applying is perpendicular, at a right angle, to the motion. Think about the Earth's gravity pulling on the moon. The pull is straight towards the Earth, but the moon is moving sideways, orbiting around us. Because those two are at a right angle, gravity does absolutely no work to keep the moon in orbit. Isn't that wild? Now, what's really interesting is that work isn't just an on or off switch. It can be positive, negative, or zero, depending on the direction. So when you push a box forward, your force is in the same direction as the motion. That's positive work. But something like friction is always trying to stop the motion, so it does negative work. And what about gravity? Well, it's pulling straight down, which is perpendicular to the forward motion. So in this case, it's doing zero work. So think about it. When you do that positive work on an object, when you push it and it actually moves, you're not just changing its location. You're giving it something. You are literally transferring energy to it. And that energy of motion has a name: kinetic energy. This is kinetic energy. Anything that moves has it. The formula is pretty straightforward. 1/2 times the mass times the velocity squared. Now that little squared part, that is a huge deal. It means if you double an object's speed, you don't just double its energy, you quadruple it. It's why a tiny but super fast-moving object can have a massive amount of energy. And this is where the scale of this stuff just becomes mind-boggling. Just look at these numbers. A speeding bullet has about 1,000 joules of kinetic energy. A car cruising down the highway? Over 500,000. And then there's our own planet Earth, hurtling through space. It has a staggering 2.7 times 10 to the power of 33 joules of kinetic energy. The numbers are just astronomical. And this is where it all just clicks into place. The work-energy theorem is the bridge that connects everything we've talked about so far. It basically says that the total work you do on an object is exactly equal to the change in its kinetic energy. You want to make something speed up? Do positive work. Want to slow it down? Do negative work. It's a perfect, direct relationship. But you know, energy isn't always about things zipping around. What about the energy that's just stored up, waiting to be unleashed? Well, that brings us to our next stop: potential energy. You can think of potential energy as work waiting to happen. When you draw back a bowstring, you can feel that tension, right? That's you storing energy in the string, which then gets unleashed as the kinetic energy of the arrow. On a much, much bigger scale, when tectonic plates get stuck along a fault line, they build up an incredible amount of potential energy, which is then catastrophically released as an earthquake. The type of potential energy we deal with every single day is gravitational potential energy. Every time you lift an object, you're fighting against gravity. You're doing work. And that work doesn't just disappear. It gets stored in the object as potential energy. The higher you lift it, the more energy it has, just waiting for you to let go so it can turn back into kinetic energy. And now for the grand finale. This isn't just some clever idea. This is one of the absolute bedrock laws of the entire universe. It's the conservation of energy. The law itself is so simple, it's actually beautiful. Energy cannot be created and it cannot be destroyed. It can only be converted from one form to another. That's it. In any closed system, the total amount of energy is always constant. It can shift from potential to kinetic and back again, but the total in the energy bank account never, ever changes. Let's just watch this happen. Picture a ball at the very top of a cliff. It's just sitting there, motionless. Its kinetic energy is 0, but because it's so high up, its potential energy is at its absolute maximum. Right now, 100% of its energy is stored as potential. But the moment it starts to fall, look what happens. Its height goes down, so its potential energy drops. But it's picking up speed, so its kinetic energy goes up. That stored potential energy is being cashed in for the energy of motion. Halfway down, it's a perfect 50-50 split. And this is the perfect finale. Right before it hits the ground, it's at its lowest point, so its potential energy is pretty much 0. All that stored energy has been cashed in for the energy of motion. It's now 100% kinetic energy. From top to bottom, the total energy never changed one bit. That is conservation in action. And this simple idea is at work everywhere all the time. The potential energy that was stored in fuel becomes the kinetic energy of a moving car. The potential energy in a storm cloud becomes the kinetic energy of a raindrop. The universe isn't losing energy. It's just constantly moving it around, changing it from one costume to another.
Okay, so we've got a handle on work and energy. But there's one last character in our story, and it introduces a brand new idea: time. This is power. Power doesn't care if you can do the work. It asks, how fast can you do it?
So here's the formal definition. Power is simply the rate at which you're doing work or using energy. We measure it in watts. And 1 watt is super simple. It just means you're using 1 joule of energy every single second. And this is so intuitive. Think about it. Both of these people are doing the exact same amount of physical work, right? They're lifting the same body weight up the same 4 flights of stairs. But the person who sprints up does that same work in much less time. That means they have to generate way more power to do it. It's why we call a sprinter powerful. It's literally true. And just to connect this to something you definitely know, let's talk about horsepower. You hear it all the time for cars and engines. Well, horsepower is, you guessed it, a unit of power. 1 horsepower is equal to about 746 watts. It's just a direct measure of how quickly an engine can do its work. Okay, now that we have all 3 of our concepts, let's put it all together. Let's see how work, energy, and power are secretly running the show in the world all around us. Ever wonder why a boxer's punch is called powerful? Well, our everyday language is actually being perfectly scientific here. A powerful punch isn't just about being strong. It's about delivering a massive amount of energy in a tiny, tiny fraction of a second. That's the definition of high power, a huge energy transfer in a short amount of time. Now get ready for a common misconception that might just blow your mind. Go look at your electricity bill. You'll see you're being charged for kilowatt hours. Now, because the word watt is in there, almost everyone assumes they're paying for power. But you're not. A kilowatt hour is a unit of energy. Let's break it down. Your 100-watt light bulb uses power, that's true. But if you leave it on for 10 hours, you've multiplied that power times time. And power multiplied by time gives you the total energy consumed. In this case, 1 kilowatt hour. And get this, 1 kilowatt hour is the same as 3.6 million joules. So when you pay that bill, you're not paying for how fast the electricity is flowing. You're paying for the total amount you've... Now, when things collide, physicists like to split them into 2 basic types. In a perfect elastic collision, kinetic energy is conserved. The classic example is 2 billiard balls clicking off each other, with almost no energy lost. But in most real-world collisions, like a car crash, they're inelastic. A ton of that kinetic energy gets converted into other things, like heat, sound, and the crunching of metal. But, and this is super important, in all collisions, elastic or not, another quantity called momentum is always conserved. This leaves us with one last big question. If energy is never lost, where does it actually go when a car slams on its brakes and screeches to a halt? Its kinetic energy clearly goes to 0, but that energy didn't just vanish. It was converted into heat in the brakes, into the sound of the tires, into other forms. It just proves once again that energy never really dies. It just changes its costume.